Thank you, Andreas. Good morning, everyone. Welcome to our VirtualWind IV conference. On behalf of Andreas and myself and colleagues, delighted to have you on board this morning. I'm just going to say a few words, then hand over to Andreas, and then we'll begin the programme in earnest. So as you can see, we've got a major focus on blades and turbines this morning and larger components, which I find really exciting. It's the true direction of where this industry is continuing to head. So I just want to say the continuing trend for larger turbines to reduce the cost of energy is pushing blade manufacturers to create increasingly long blades. Manufacturers must innovate then in every area, from materials to design to manufacturing methodologies. Larger blades with extensive use of carbon fibre are much less tolerant of manufacturing flaws, so materials and process engineering is crucial to future success. Modular blades offer the possibility of assembling blades from smaller components which can have better quality control, and we're looking at this as part of the Horizon Carbo 4 Power project. In addition to the cost pressures on manufacturing, there is an increasing push towards sustainability and the circular economy. At ORE Catapult, we have now been involved in several projects in this space, such as CEST Wind and the Cornwall Flow Accelerator project, which is looking at reducing the amount of embedded carbon in blades and other turbine components. Additive manufacturing is one of the most promising avenues for reducing waste and developing structures which would otherwise not be feasible. There are many potential applications for wind turbine blades, from creating molds for components to creating the blades themselves. This area needs a lot more research and applied research. ORE Catapult has recently invested in an additive manufacturing cell to start investigating the possibilities that additive technologies enables, as well as funding a PhD through the Wind Blade Research Hub into structural optimization of blades, creating useful additive manufacture. And I know lots of people are doing similar things, and it's really good that this whole new space in science has been explored deeply. An important stepping stone towards implementing new manufacturing processes is validating them, with testing a crucial part of the picture, all the way from coupon testing through subcomponent testing and finally full-scale blade testing. ORE Catapult continues to invest heavily in the development of our blade test offering. So we're really pleased to be working with Fraunhofer colleagues and others in the research space around the world and around Europe for these critical endeavours in the pathway for future success of offshore wind, where, as I say, components are getting ever bigger, but ever more complicated to be manufacturing and delivering efficiently and robustly. So, Andreas, with that, that's my opening comments. I'll hand back to you, and good luck to everybody in the conference today. I know it's going to be really interesting. Thank you very much.
Thank you very much, Andrew, for this introduction, and also a warm welcome from my side to everybody listening in today. It's a pleasure to have you all here today. And yeah, Andrew already talked about the challenges of the industry, and of course also from Fraunhofer we have pretty much the same view on all these things. And I find this opportunity always very interesting to listen to you, Andrew, and I think we should talk more frequently because we do a lot of things in the similar area, and I think we should do things more often together. But at least I think we are running into the same direction. And also on our side, blade testing is of course a big topic, also testing of these very large blades, where we're investing in a new test facility for blades which are way longer than 100 meters. Their construction just started, and we will be ready next year to test the first very, very large blades. But also all these other components, all these huge machines are of course big challenges also for us as Fraunhofer, coming from the validation testing side. And so enhancing our capabilities in virtual testing, digital twins, and so on is of course these are areas which are of great importance for us to make sure that we have the right offerings there. With this background, these virtual conferences are of course also very important to us to get a better understanding what's going on in the industry. And I'm very delightful to have interesting participants from the industry sharing their knowledge with us today. So that's great to have you on board. And I think it would be an interesting morning or half-day session And I'm very happy to have all the participants, all the presentations here today. So thank you very much for that. I have the pleasure to hand over now to Dr. Steffen Czichon, our head of the Rotorblade department, who's going to be our host today and is leading us through this session. And with that, again, a big thank you for everybody being here, for preparing the presentations, presenting today, and all the audience listening in. And with that, I hand over to Steffen. Thank you very much.
Yes, thank you very much, Andrew and Andreas, for setting the tone of today's conference. And also from my side, a very warm welcome to this conference. I think everybody in the audience is pretty used to doing virtual conferences by now, even though we all miss the real ones. Without much further ado, I would like to introduce the keynote speaker for today, which will be a real pleasure. The keynote speaker will be Carsten, or is Carsten Burchardt. He's an extremely interesting speaker because he has an extensive background of more than 20 years of experience in the area of product lifecycle management. He is currently the head of research and development with Siemens Digital Industry Software, so not Siemens Gamesa, the wind branch, but Siemens Digital Industries, and also responsible for strategic business consulting. In addition, because of course that's not enough to do, he's also professor for product and system lifecycle management at the Otto von Guericke University in Magdeburg. And I'm extremely excited for your presentation, Carsten, because I'm sure you can bring in the perspective not only of the wind industry, but also of other industries. And I'm really looking forward to your presentation. So Carsten, the floor is yours.
So, could you hear me? Yes, it's fine. Warm welcome from my side too. Yes, thank you, Steffen, for the introduction. I would like to give you a short overview because I'm working at Siemens, and Siemens, as you know, is working in different areas, not only in wind power. And so we have a big experience international, and one of the general challenge from my understanding will be that, oops, it was too much, sorry, was that the complexity is changing. That means in our world where we are living today, we know about globalization, we know what was happening about the acceleration with COVID. That means regionalization is important too. So we have two different aspects we have to deal with them. The other one, networking and flexibility, is really important. If I think around 10 years ago, I asked my company, is it possible to work from a home office? They were not so really happy about them. Yes, could we control these people? What's happened with their work? How they work together? Whatever's happened. Now COVID was running. And from our understanding, and I'm working in an area of digitalization, we foster digitalization is important. There's a big growth in this area. But because we are running in this area, clients are not looking like they have done in the past. It means cost is really important. Return on investment for the solution. They would like to show or have to look for these things. So it's not so easy to deal with these things, but of course we find a way. What changed in the wind farms? If we're looking for the wind farms, from my understanding, there's a change. First of all, we are running from land farms to offshore farms. That means there's a completely new requirement which we have had. In the past, with the other one, with the land one, from my understanding, if I look for Germany, a lot of these companies that were running were, I would call it semi-professional. Sometimes from private people, and they're working in this area. But after a while, and when we find out we have to go offshore, and this was forced us from the government, that means here we have to have a professional environment. an environment which need to ramp up a large design and a higher quality, and more power is necessary. And the next question is, what's happened about our life cycle costs? Yes, the engineering is not the same like we have had before. You see the right picture. If I remember, in 1985, Vestas developed wind machine. The blade diameter was like 50 meters. They have 55 kilowatt watt. That's not so much. And if you're looking for the right one now, in 2019, General Electrics, they have had their first prototype. It's called Additive, and Vestas with this M236. They have a rotor diameter of about 236, and this means 15 megawatt is running now. So completely changed how the industry have to fulfill these requirements. If we look for the, I will call it the general construction for wind turbine. And here's an example from Samset, and of course there exists other one. We would like to divide them in, we have the generator, we have the gearbox, the tower, it's running from along, the tower, the bedplate mainframe, the disc brakes, and slip clutch, the rotor shaft, and blades of the rotor. For us, it's important in this conference with IWES, we are looking only for the rotor. What's the consideration of the product lifecycle costs? There exist different views. If you are looking for the manufacturing cost, that means by thinking about what's happened about the material, what's with their labor, their production, with their logistics. They are the blade manufacturers, and as you know, 80% of the requirements we have to fulfill afterwards are inside in the development phase. So they are important for the completely life cycle of this farm. Then you're looking for the maintenance cost. These people are looking for the inspection. What's happened about the downtime? Yes. What's happened about if we have a replacement? And after the decommissioning, crane, transportation, co-processing, cement, do we have to use them? How we could recycle it? And what's happened behind is the idea that there's the clear shift offshore to the wind parks, but the logistic and the investment which we have had isn't the same. There's a completely other capex we have to think about. At IWES, together with other companies, we are looking for the impact on rotor blades. The impact means we are looking for two different models. One of them is the 40 meter. This was used, most of them, for onshore. The other one is the 80 meter. It could be 80 meter and more, of course. And the challenge is if you're looking inside in the building, 40 meter is a really huge, big one. It's not so easy to produce them. So this 81 was a scale one. The challenges of the different were with the 40 meter, there was a serious size. It's possible. We have a constant quality and we can look about the manufacturing cost. If we go forward for the longer one with 80 meter, there's a completely other way about the manufacturing. Think about people, they have to manufacture, their arm length is not long enough to go inside and to work there. And we have to increase the quality. Highly quality is from the customer necessary. They need a robust process for reproduction of high quality, and important for them is to reduce their work for mode and machine for occupation of the times. New process required, and of course a cheap material for the performance. And think about what's happened is if a Rotorblade fails, yes? Think about the downtime, the root causes analysis, the reinforcement of similar blades on sites, and all the challenge for the sales team. They have to think about how they go forward, which material they have to use. That was one of the reasons in 2012, different companies came together and said it will be good if we work on an environment which is fostered from the government. They paid money and we called them blade maker. So some key facts about blade maker. As we said, established in October 2012, running close at the half 6 years to March 2018. 16 partners, and you see a list of them there with their icons, were inside. And this was really important. This research project was fostered or funded from the government, from Germany. 30 million, yes, of course, that's a lot, but we need them. And we built up a completely demonstration center for this automatic production in Bremerhaven. That was the beginning of the blade maker, of course, was a little bit earlier. It was 2 years earlier. That means it was generally important that we know for industry, it's not so easy to do it. There's a lot of cost you have to handle with them. And of course, you need the research. There should be a transmission from both between industry and research. Some results of our blade maker project. As you see here in the picture, we built up a demo center in Bremerhaven, and we need novel direct tooling. And interesting is the adhesive application and fabric layout, and we implemented a direct infusion. And most important at that time was, of course, for us, I will call it completely CAD/CAM process to deal with them. We want to have the end-to-end loop, and that was a good, I still think from my understanding, the only one from which I know which was really realized between industry and like an institute like the Fraunhofer. So direct tooling for making own molds, experience with automative adhesive application and fabric layout, direct to infusion, and the CAD/CAM process. But of course, whatever's happened once a day, the things go over, and we said we have to start with a new one. This one is called this research project Blade Factory. And of course, first blade maker, then blade factory, they runs together. We start with them in October 2018. Again, 12 former partners still were inside. Additional, these things was founded from the government, 9.2 million. And again, the project leader was Fraunhofer. For us, it's important to deal with, I will call it manufacturing process. We have two parallel manufacturing machines. They are working, they are measuring, and it was important for us to speed up the infusion and curing process, because it's a lot of time you have to invest here in this area. When we make our manufacturing at IWES, and if you're looking for the Rotorblades, here you see important for us is the cost analysis. Why about the cost analysis? As you know, if you're looking about service, the price running from west to east is different, yes? You have to pay a lot of higher for the same service if you go to Asia Pacific, as an example. So the only thing where we can make innovation for technology for us forward is in the process, to standardize the process. So we use different materials like glass fiber, balsa wood, epoxy adhesives, and we find out that when we look inside, that's on the next slide, and we look inside for the cost, that there's a completely different scenario. As an example, the price for 40-meter blade only for material was more about 31,000 euro. That means 45% of the completely price from the blade. If we complete this with the other one, with the 80 meter, you see it's on the right side, then it means here we paid more than 186,000 euro, and these are 70%. This means for us, the material price to reduce them is really, really important. We need a closed loop for an integrated process chain, and of course, to use not only the conventional production, you need a new production for larger blades. And I know Peter afterwards will talk about new materials in his presentation. What does it mean for us? From my understanding, if I have a view back on the first project or the second project, we need an integrated framework if we are working in the wind industry. A framework which will guide us first for virtual prototyping and later on for virtual and physical testing. Here you see different areas we have to address. Of course, we have to know about the objective, the design, the design variables, the design system level. And then we have to think about inside in our wind farm, what is important for us. From my understanding, a good idea to do this is to work with a digital twin. The digital twin is an interesting idea to make a combination between the virtual product and the virtual production. So it means, yes, you have your specification and the verification, and you can use after you have done the virtual production and start with a real production, with an automation process. And if this is running, after a while, you have a real product. We are working with digital twin, and it's called in other companies, maybe has another name for virtual commissioning. It's really important to know about them. And it helps us to have this, I will call it closed loop inside in the wind industry. With a look for our time, from my understanding, we are tackling in the wind energy with different challenges in the future. Looking for the quality, we know there exists single platform for both for local and for global analysis. We have different solver capability combining MBS and FEM, and we have a correct environment loading and considering on non-linear effects. Other one, we have to faster the process of model variance. That means the methods which we are using have to run quicker. We have to use virtual testing. And of course, the load case generation as per norms per certification process is important. Reducing costs. In our company, and as I said, it's not only for wind energy, if we have a solution and we would like to sell them, KPIs, key production indicators, are really important. That means we have to speak with our customer. What are the key production parameters inside into your company? And where's the correlation inside if we used as an example our digital twin? And how could we help to foster, to improve this process? Our personal background is without return on investment in the future, we can't sell anything anymore because people are looking exactly what are the requirements, which things they have to change and how they go forward. And of course, at last, engineering assessment is important. We need more faster decision. We need a bridge between durability for prediction, and of course, this will guide us in the future. I'm proud to be a member of this group because from my understanding, we are working in the area of renewable energy. As that means it's important with our innovation, our footprint on the earth, we can help them to make them thinner as it was in the past. Thank you very much. I will give back to Steffen.
Yeah, thank you very much, Carsten, for this interesting presentation and your keynote. Maybe for the audience, we have the idea that you can ask questions in the chat at any time. But what we want to do is we want to collect all questions and save them for the panel discussions. So please post any questions you may have in the chat, and we will take the questions after the panel discussion. Or in the panel discussion after the presentations. So I think, Carsten, what you just did, you posed a lot of challenges. You correctly sort of prepared the field of what are the technical challenges that we need to tackle. And I think that's a great introduction to the presentations that we have coming up, which is one presentation by Marie Hooper, who will talk about laser projection for more reliability. We will have Heiko Rosemann following her on industrializing rotor blade manufacturing. We are also looking forward very much to a presentation by Lars Windels on digital machine twin. So that's also something, Carsten, that you have mentioned during your presentation. And as you already pointed out, the last presentation will be by Peter Greaves on new approaches to novel materials. We will then have a short break, and then we will follow up with a panel discussion. I'm interested to hear all questions from the audience for that. And closing this little conference will be a session which will be led by Heiko Rosemann. He will take you all on a virtual tour to our research facility if you're interested. So now the next presentation will be by Marie Hooper. I'm very excited to hear her presentation. Marie has started her career with LAP in Lüneburg in 2006. She's a sales manager for CAD Pro laser projection systems, so she certainly knows her way around the wind industry. She's responsible for the worldwide business activities in both aerospace and wind energy. So I'm also interested to hearing her perspectives on maybe some of the similarities and differences. She has a lot of years of experience in wind power applications. So I'm really looking forward to what you have to say, Marie. And I would like to hand over to you. So the floor is yours.
Yes, hello everyone, and a warm welcome from me as well to our today's webinar. So I hope that you are now seeing my screen. Yeah, thank you, Steffen, also for the nice introduction. And if everything is fine, then I will start with my presentation now. Maybe before I start talking about laser projection system for use in the wind industry, I would like to give a small introduction to the company and who we are. So the company LAP is specialized in the production of laser-based systems with two main purposes: positioning and alignment on the one hand, and a non-contact measurement on the other. Our positioning systems are used for various applications in various industries. In healthcare, for positioning of patient during a radiation therapy for self-treatment, and in other manufacturing industries, for the laser projection systems are among others used for positioning and aligning material during production, layer process, or other worker assistance during assembly. Our non-contact measuring systems are consist of laser sensors are used to measure and control online thicknesses, diameter, straightness to guarantee the same quality during the whole production process. But I'm not going to talk about this product today. So what now I will show you also where we are based. So we're based in Lüneburg, south of Hamburg, and we have a few sales and service offices abroad to guarantee the market presence and service in the different countries, different areas. And we're also working with distributors, very qualified distributors all over the world. The company employs more than 300 employees today worldwide. So now let's go back to the to the subject. So we will, I will talk about laser projection systems, as I say, and looking at the different trends today. You know, everybody knows the growth on the market. The lengths of the blades are getting bigger and bigger. The design must be adapted. The quality requirements of the blades is getting higher. This is today the trends that we have, and I've missed actually. Yeah, we will have, the market of the wind turbines has been continuously growing in the past 10 years. The supplier of wind turbines are facing great challenges to respond to the growing demand and remain competitive. Different areas from the production to the transport, installation and maintenance would be challenged with these requirements. Turbines with more capacity must be produced at lower cost, and to increase capacity and performances, the blades need to be longer, lighter and stronger. The design of the blades continuously needs to be optimized, which request from the suppliers and manufacturers great reactivity and flexibility. The first system that was supplied, the first laser projection system was supplied in 2013, and today major manufacturers of blades are using our laser projection systems on more than 100 production lines worldwide. And the layup process is actually the main application today for which we are supplying the laser projection system. And why do we need for the layup process help from the laser projection system? Then because of the position accuracy, the labor intensive, it's very labor intensive. The risk of errors and wastage are high. You have very complex materials with multiple layers, and it's very time intensive. So the laser projection systems will contribute to a more efficient projection process of onshore and offshore blades. This is a small video to show you how it works. It's a very short video, but gives you. So you can see here the laser projection on the blade in the mold. Now I will go back. So the laser projections for wind blade production. So the laser systems project lines and complex contours onto flat and three-dimensional surfaces and make digital data clearly visible. The laser projection shows the user the exact position of the next step in the process and assures quality control. These systems render manual measuring or the use of templates unnecessary while saving time and improving quality. These are the benefits that you would get from a laser projection system used for the layer process. So you will project each layer step by step. No manual measurements needed, high accuracy of positioning, high process reliability and repeatability. The layup time is reduced significantly. Less errors, so less material wastage. And the system is very flexible and scalable. Again here, so the laser projection the laser projectors that we are using in that application are usually in green projection because it's more visible. It's eye safe for the operators. So it will show you all position for the glass fibers, center line, for instance, or the bars or other materials, anything also on the finished blades. Today, it's more used for the layer process, but we are also testing the lasers, to position the vortex on the finished blades. It's also used before to prepare all the materials on cutting machines, for instance, stitching machines, to prepare the kits also of the materials. Here I show you a layout example, a typical example with the downwind and upwind molds. And above these molds, you will see the laser projector installed. So the number of the laser projectors will be calculated in accordance with the height, with the length of the mold. This planification will be done together with the customers. We will get all the information about the mold's length, the shape, the height, the roof structures as well, because we will usually fix the projectors onto the existing structures if it's convenient, if it's suitable. If not, then we will also plan some structure beams or other supports to get the right position for the projector. I would say for 50-70 meters meter blade, we will use approximately 7 projectors per half mold. Also in the root end, as you know, the curvature is extreme, and here we will have 2 projectors on the side for a better coverage. We will also here, we will have also 2 projectors due to the amount of data to project in the root end. It's a very complicated area with more layers, and this has to be done with 2 projectors. Here I will show you a small film how to operate the systems. There's no sound, but I will explain to you. So you see here a section of a blade. You see 2 projectors, and in the middle is a camera, but I will not talk about it today. So we start the software. You can see here some targets that we have positioned around the mold. This is needed to calibrate the systems in the first place. And here we open a file, the projection file from the customer. So here you will see the center line. So the different layers. Each step of the layer process is done in different layers. So here we project the center line. It's a bit flickering due to the probably because we have also some text projected at the same time. Yeah, you go step by step through your file, through your projection file, and position your material. There's some baza wood. It's not exactly like the way you do it, but it's just an example to show you how we position how it works. And yeah, and then you will go then step by step and follow your layer process so that there's no layers missing, and it's very easy also for the worker. So this is the projector. It's a very small projector, 3 kilos, very small size, very easy to put up, to mount. The accuracy usually used in the wind application is 0.2 millimeter per meter distance. The 0.06 millimeter is usually used for the aerospace. We use diodes as laser source, and it exists in red, green, yellow, well, red, green diodes. And if you put 2 diodes in one device, which is possible, then you get 3 colors, red, green, and yellow. Yellow is the overlapping of red and green. The laser power from 5 to 30 milliwatt. And in the wind industry, because of the mounting height of the projector, the distance between the projector and the surface, we will usually use the 10 or 30 milliwatt laser power. Of course, according to the laser power, we have different laser classes, 2M or 3B. This is the Prof that we are supplying together with the hardware. The software with integrated help available in different languages, and the software will support different formats, different data formats, from DXF to IGES. DXF and IGES are the most common in that application, but we can also support other formats like STEP with an additional module, or CATIA as well is also possible to project direct, or you can also export the CATIA into an IGES or another format that we support directly. The software is possible as a single task or multitask. Multitask means that you can open different files with the same software, which is most of the case in the wind application, because we will work on the upwind and downwind at the same time, but not at the same time, but not at the same pace probably. So you can open with the same software a task for the upwind and another task for the downwind. These are the benefits at a glance. So thanks to the laser projection system, you can achieve higher throughput. The time that you used, to make all the manual measuring is gone. So you will really save a lot of time in the production. We reckon that you can build maybe one more blade or 2 more blade per week, which is quite a lot. and you get improved quality. The material is placed more accurately on the blade. You will use also less material, because you will have maybe less overlapping of materials. You have much less training time. The staff is trained very fast, and I know that in your industry the staff is changing quite a lot, and in that case, you don't need to. It doesn't need to go through a very long training. It can get a remote control in the hand and go fast through the layout process. Lower cost, of course, because you get less wastage. I mean, if you are missing, if you are some material or if a layer or something like that, then you have to start again, and this is something that is not happening then with the laser projection systems. These are our major customers in the wind industry. LM, Siemens, TPI. They are using today our laser projection systems mainly for the layout process. And it's it's more than 100 lines globally, and it's getting bigger and bigger. And this is today the trend. What I would like also to add is that what you need today is a lot of flexibility, because I'm saying that with the customers, they are always, the mode is changing every month. They will want to fulfill, to respond to the demands, and this means that if today they are producing a 50 meters blade onshore, or another longer blade for offshore, but then the next month, they might need, to change and build longer blades. In that case, I mean, the laser projection system that is installed can be adapted, can be easily moved to another position as well, or can be extended to fit the new lengths. And I think this is something that that's a very good feature, and very good something that you need today to be flexible and respond to the demand. And that's it. And I thank you very much for listening.
Yeah, thank you very much, Marie, for this interesting presentation. And I think you were perfectly on time. That's not always too easy to achieve. So excellent. Thank you for that. And again, I think let's keep the questions. You can write them in the chat, and we'll take the questions in for the panel discussion. And now it's my pleasure to introduce my colleague, Heiko Rosemann. Heiko has been working with IWES since 2011. He started out in blade testing and saw the light after a while, and is now working on blade manufacturing. He was heavily involved in building up the Blade Maker Demonstration Center. And I'm really looking forward, Heiko, to your presentation on industrializing rotor blade manufacturing, large-scale research. So I think you are going to present some of the research activities that we are running in this field.
Yeah, exactly. Thank you, Steffen. I'm afraid I probably won't be on time, but we will see how that goes. The aim of this presentation is to give you an overview of what we've been doing to address the issues Andrew and Carsten have given you an overview earlier. So Fraunhofer IWES, it's just one slide. So we do basically everything around wind. We start on the meteorology side, wind field site assessment, CFD, aerodynamics, nacelle testing, so the hub and the electrical side, certification of the electrical characteristics. We also do field tests. So we have a group that's climbing up onto wind turbines and installing sensors there. We test the drivetrain components. We test the large bearings. We test support structures. We're also going into hydrogen currently. And the part the part of our department that I'm talking about is the qualification of composite materials and parts, starting from coupon testing all the way to full-scale blade testing, but also the very important part, composites get their properties from the manufacturing. So the manufacturing is a very important part. Yeah, we've already seen the left part of the slide, the manufacturing cost analysis by Carsten showed. This is for the IB40 rotor blade. That's an EWES blade design, so we can go that deep into the material. We can say, okay, if we need another meter of infusion material, another meter of hose or pipe, it's going to cost €3 more per blade, and then we'll have 730,753 euros in that blade. Breaking that down, large part is fibers, resin, core materials, and consumables like the vacuum bagging and resin uptake materials. So that's what we always have in the back of our heads when we're talking about industrializing manufacturing. If we want to reduce costs, that's where we need to go. One thing that is very hard for us to really determine is the costs of bad quality. So most manufacturers have had these issues. They're not that often, but if they happen, it's obviously a huge impact on all these costs, and basically you can throw this out the window and start anew with a new cost calculation. Somehow I was missing a slide there, sorry. If we group this by manufacturing steps, we see the shell production in the main mold has a huge part of the material cost. That's the core materials. We see on the shear webs, main spar cap, the fibers, and then we have a large labor-intensive part in the machining and surface finish. It gets even worse for longer blades. When we have carbon fibers, the material costs go much higher. So what do? We're looking into core materials. That's why I'm also very, very interested in the talk Peter is going to give later. A typical part of the blade on this 40-meter blade maker blade, IB40 blade, is about 1 meter by 1.6 meters. And we're the classic way is to get some pre-made kits with these kinds of slots, and then just have someone drape them in there, maybe cut them to shape. We're looking into replacing the PVC or PET with a PU foam that could be made directly to shape in the mold. We're also varying the slot patterns to improve the infusion, and also this the resin that goes into these slots will have different will change the behavior of the entire sandwich. So we can adapt the material parameters to what's actually needed in which part of the blade, like here or more in the root. This is a picture of our additive manufacturing tests we've done. I will show you the results later with the camera when I'm going through the demo center. We're also looking into direct tooling. So as Carsten said, that's one of the results of the blade maker project. And we also want to try to print the molds with this approach. What we're also thinking about, so if I say outlook, this is really not something we're going to do tomorrow, but it's something we have in our head and are planning for. Maybe see if we can get a thermoplastic foam. So I don't know, something that's that could be reused together with a thermoplastic resin, infusion resins, to have a better recyclability. We're looking into replacing balsa wood, and we've done some first tests with probably balsa wood. The first approach is a different kind of wood. The next approach is to find a more consistent material. Yeah, and we've done the first test to recycle balsa wood from decommissioned blades and reuse it. We'll see how we get that going in the future. We're looking into the fabric placement for the root. Okay, when I tried this earlier, there was an animation. Why doesn't that run now? Yeah, so anyway, we're picking up the fabrics from a flat rectangle, shaping them with this end effector and placing them into the blade root automatically. Offline programming, Lars from SWMS will show the more details of the offline programming, that there's no teach-in. We can do a pre-simulation of the approach. Yeah, we will see more of that later. We are also going into new gripper concepts for multi-layer gripping. So the other one we saw had vacuum grippers. It's can only take one layer of fabrics at a time. This one's gripping, I think, up to 15 layers of fabrics, or also core materials, as you see on the right. Yeah, all to speed up the layup process, the fabric placement, and make it more precise and more, well, at least consistently precise, to have the machine's going to work the same on Monday morning or on Friday evening. Workers don't always do that. I know I don't. So we're also doing fabric placement for the entire shelves. The one I showed before is more like a single ply placement in the root. We're doing that together with the University of Bremen with the BIC. They call it the direct textile placement process. We're integrating that into our demo center, and again, we have a virtual process next to it. So we'll see more about that later. We're working on Pultrusion for the main spar caps. That's where most manufacturers are going these days, because well, you have less waste material. It's a huge impact on the costs, especially if you're talking about carbon fiber pultrusion. We get a better utilization of the actual material properties because they're produced under tension. So there is no waves at all, no undulations at all. And yeah, if you have these pre-impregnated, pre-cured profiles, we also have a consistent quality again. Yeah, we also do injection simulation and validation. I'm going to show you on the next slide our small pultrusion machine. Well, was born as a pre-pregging machine. We're adjusting it to be able to pultrude parts. So we get all the fabrics coming in from the left, going through the cavity, where we validate our infusion or injection models. And yeah, we get some nice pultruded parts, GFRP, CFRP. We're also thinking about thermoplastic resins again there for recyclability. So yeah, we're getting some very interesting, or very much looking forward to the results we'll be getting there. Then we have a large step about the adhesive application. So the blade's built from a couple of parts that are glued together. The left shows the classic approach where someone walks around with basically a hose where the adhesive comes out, and another person runs after him with a template to draw away the excess adhesive and shape the glue line. We've developed a automated or semi-automated placement head that basically can shape different materials, different shapes, different cross sections of the adhesive bead. Yeah, just with the tip of a finger, that one changes, and so we get a more consistent and less excess waste, quicker process, cleaner process. We can easily integrate that into an automated manufacturing process, but also in a classic hand manufacturing process. It's very easy to clean that one, and when we're measuring in advance, we can go even further down with the excess adhesive that's applied to just make sure if we have a tolerance of 10% thickness, we need to apply 10% more adhesive. if we measure that in advance, we can only do that where we really need it. So then there's another process after gluing, after closing the mold. We're looking into the surface activation and grinding, which is a labor-intensive process. Sorry for the typo. Shaping the trailing edge and the leading edge contours for the very important for the aerodynamic effects, and also activation of the entire surface for coating. We've done some tests with these test fluids to show the effect. We're working closely with our rain erosion and coating test stand to validate the results we're getting here, and implementing new grinding and activation technologies into. This is made for our automated machine. We already talked about, or Carsten already talked about a bit about the direct tooling with integrated heating and cooling options. The basic step is we get some PU foam blocks, or maybe later 3D printed foam blocks, mill them with the cooling channels, several different zones. This is a test part, so we were evaluating the efficiency of the cooling. The heating is done through carbon fiber mats infused with surface layers. And then we have a demonstrator of that. Yeah, we can see the different cooling concepts and the results. So pretty consistent temperature. The right side, I think that was the larger channels, has a much better cooling effect. And we're going to build a larger part to larger demonstrator for that to also then influence the infusion with different cooling fields that will influence the infusion process. Where do we do all that? That's our Blade Maker demo center. I'm sitting in the control cabinet right now, and I'll show you later on that virtual tour. We have a double gantry system, CNC controlled with the Sinomeric 840D. As you can see on the right, it's about 30 meters in length, so we can make 30-meter long parts. Can run at 150 meters per minute, which is really quick, especially for a 2-ton machine here. It can carry 400 kilos per head, so we can have our special end effectors, 6-axis with 6-axis movement and 6 degrees of freedom. We have a heavy-duty platform that can travel along with the long axis, so we can have material mixing and dosing equipment on it. We have that in the hole to apply adhesive, to 3D print foam, to infuse the dry layers. We have quite a bit of capacity to store hazmat, so all these resins that are, you can't just place them anywhere. We have some measuring tools, and we also have an automatic fabric cutter to produce basically what's later laid onto these nice laser projected lines Marie showed us. We don't have a laser projector yet, but I bet that's going to change pretty soon. That's one side. The other side we're operating right now is our Lamverde facility, where we are building full blades on the 30-meter blade. We call it IV30. We have our own structural design on that. We do that to research quality control. We try to find effects of defects. So we actually build a blade. We build some defects into the blade. We put some sensors and measuring equipment inside. We have a full mold set, so we can build the blade. Actually, we're trying out new materials there, sometimes for research purposes, sometimes for customers. And we're going to investigate recycling there too. Basically, it's a large hall, a mold set, and then we can do whatever we want to do with that. Run and go. A few more impressions. So this is from the blades that have been built, I think, a few weeks ago. The molds, everything's set up nicely. One of these projects, as I said, was effects of defects. So we manufactured this spark cap to actually have a wave. We're going to test that on our full-scale blade test stand and see, if this actually is the place where cracking or delamination start, and how fast, how much impact it has. This is glass fiber, so it's probably not going to be as bad as with carbon fibers, but yeah, I'm sure we will see something. This is another defect we're investigating. We basically have the glue line on a plastic foil, not attached to the shell. So the spark gap will be floating for the last, I don't know, 3 meters or so. We'll see how that develops in the blade test as well. Yeah, okay, that animation works. That's nice. We're also doing quality control and material characterization there. We have this half bowl to investigate the draping properties of these NCFs. We can measure the fiber orientation and the results of this and compare it to the simulations. And on the right, that animation that's monitoring the resin infusion right now, starting very hot over here, floating all the way to both sides. And the temperature scale will switch in a minute. Then we can watch the curing and the curing process, especially in the very thick parts where the material generates a lot of heat, and monitor that, make sure it doesn't overshoot with an infrared camera, or I think we have 2 or 3 on top of there actually, and that's cut together. So we've seen, to conclude this, we've seen it's a highly competitive market. We've seen that more in the keynote speech than in what I've said so far, but yeah, it's also our approach to that. So we want to reduce blade manufacturing and also service costs. So we need robust processes to have a high quality, constant high quality. We need to utilize the material to its fullest. So if you get the fibers in the exact correct orientation, get exactly the amount of adhesive we require. And we're looking into process that reduce the work effort and the mold or machine occupation times, like preforming, fabric lab, surface grinding. But the large impact will be from the material side. So I think on the first one. Our cost model can give us answers. So these pie diagrams I showed in the beginning, they're from our cost model. They can answer the question, how much invest can we afford to save this kind of money or that kind of money? We can do full-scale tests with the IB30 and the IB40 blade designs. We can investigate on the IWES wind turbine 7.5 164 blade design. So that's an 80-meter blade developed in a different research project. We have the structural models. We can use them for basically whatever ideas we can come up with, investigate what happens if we change this fiber, exchange the glass fiber with, I don't know, natural fibers. We can simulate that, and we can do real tests on the IB30 and on the first part of the IB40 blade. So our demo center is large enough for that. What are we going to look in the future? What are we thinking about right now? What will be the big things for the next 3 or 5 years? Well, processes and materials for built to recycle rotor blades. So far, we've always talked about manufacturing and service costs, but now in Germany, for example, the feed-in laws, the first feed-in tariffs are 20 years old now. So the first bunch of blades is coming down pretty soon. They've reached their 20 years of lifetime. And yeah, in the future, we're going to need to build our rotor blades to be easily recyclable. On the material side, maybe on the design side, we will see. Yeah, and we're looking into implementing a digital twin of the blade and of the machine for process control and quality assurance. I'm sure Lars will show a little more of that. And thank you for your attention. Questions, as Steffen said, I'd like to hear them later. Looking forward to hear them later in the panel discussion. Thank you.
Yeah, thank you very much, Heiko. And also thank you for doing my job and telling people to not ask questions, or they can ask questions now, of course. So please feel free to do that, and we will answer those in the panel discussion. And Heiko, thank you also for being perfectly on time, even after announcing in the beginning that you are not going to. I now have the pleasure of introducing Lars Windels. Lars is the co-founder and Managing Director of SWMS Systemtechnik. He is working on the digital process chain of highly specialized manufacturing processes and machinery, both in aerospace and wind turbine production. I'm really looking forward to your presentation, Lars, to see what your version of a digital production chain is. So Lars, the floor is yours.
Thank you, Steffen, for the very nice introduction. Just a second, I will share my screen. Okay. I would also like you to welcome to the VirtualWind conference, and I'm really looking forward for a lively exchange with you in the panel discussion. As Steffen mentioned before, my name is Lars, and I'm the Managing Director of SWMS. Our company is located in the northern part of Germany, in the very nice town Oldenburg. I think since 25 years, we have been dealing with the digitalization of manufacturing processes. And so about 5 years, we have also been focusing on the production of large components, and in the special case in Rotorblade production for the wind energy sector. Today, as Heiko and Carsten mentioned before, I will tell you something about the usage of a digital twin, digital machine twin, and I should say digital twins along a multi-process chain, because I will tell you something about a machine twin, a product twin, and a process twin. First of all, here you see my short agenda. Till the begin, I will tell you something about the CAD/CAM environment we have established at the Blade Factory project. And after that, I will give you our understanding of digital twins, as well as how to use them to optimize the manufacturing of rotor blades. Okay, let's briefly start with the CAM process in the Blade Factory environment. Here you can see the whole or the entire CAM process. It starts on the left side with the component design. Here we use a FiberSim from Siemens. Then comes the phase of production planning. Here we use our software, the CEST tape station. Based on this, a process simulation is carried out. And the last step, you see it on the right side of the slide. We check the generated NC code against the virtual image of the machine, and the so-called VNCK. VNCK is a virtual NC kernel. It represents the Siemens 840D control unit. Here we see the component design, especially here for the rotor blade. You can define special zones. You're able to create special layers. And each of these zones and layers are assigned to a specific manufacturing process. I come to this a little bit later. Here we see a little bit more in detail. Here we see the entire layer structure, how it is we will designed in the FiberSim toolset, and the resulting geometries we are exporting at the end. And there's special FiberSim export includes surfaces, contours, and material geometries. We all are exporting and then using it for the next process step. In this picture, for example, we see the first ply of an ATL process. ATL means here automated tape laying. It's a fiber placement process. And this design manufacturing areas, we import in our software, the CEST tape station, and use it directly for the CAM programming. It's a representative of so to produce a part. And so we are able to create a production planning, and that can take place on this basis. A little bit more in detail. We have specific process parameters for every production step and manufacturing process. The specific manufacturing processes can now pre-created in this CAM environment. Here shown for example, at the 88 process. And it is possible to create individual approach, retract movements of the operations. You can parameterize the operations. Likewise, it's possible to perform the entire operation definition. Here it's shown in the picture. For example, in the case of fiber placement, it could be the minimum toe length, approach speed, and all these relevant parameters for the manufacturing process can be specified in this area of the software. When the operations and the processes are all specified and configured, or I should say maybe programmed, it is possible to simulate the whole process. And afterwards, we are able to generate the NC code for the machine, here for the Blade Factory demo center. And you see here in the middle the anti-factor for the ATL process. The anti-factor is the head which will lay down the material on the form. And here we see concretely the simulation of the path of the tape and the deposition of glass fiber material. There are many other processes. Here on this slide, we see a second machining process. It's a so-called directed textile placement, or in short form, DTP. In this process, the material is draped into the form tool via 7 slide modules. It's a little bit like you push it with your hands. I would like to highlight here that we are managing and simulating over 30 axes at the same time. That's really a lot of axes we are simulating at the same time. So in addition to the machine, we are also simulating the movement of all individual axes of antifactors, like here the DTP antifactor. It's a really complex antifactor, and so it is necessary to simulate all axes to create a good simulation result, especially for the draping process. Here we see another process. This is used for the production of the Rotorblade root. Here we see that previously tailored material layers are picked up by this pick and place antifactor, and it's an usual pick and place process. So the fiberglass layers we are previously planned in the Siemens FiberSim environment are created and laid on in that way here. And after that, when all processes are programmed and created in independent NC programs, we are able to address all process steps in the NC programs. Here we see it on the right side, the NC program for special antifactors. And so we use integrated post-processor, or processors, I have to say, especially adapted to the processes, for the antifactors, to generate specialized programs, like for gluing programs, for milling, for sanding programs, etc. Okay, let's have a little bit deeper look at the advantages of the usage of digital twins. First of all, I would like to show that there are different digital twins. On the one hand, on the left side here, the virtual twin of the machine, which I just described before. And on the other side, the virtual twin of the component, of the product we want to build, or which we want to manufacture. So let's start with the machine twin. First of all, we use the virtual image of the real machine controller. That's really important. With all its settings, axis, tools, frame offsets, and so on. That's important that we have a real representation of the machine. It's not an emulation, it's a real simulation. That is why we also speak here of the digital twin of the machine. In addition to the controller, the entire CAD description is also used for the simulation environment, so that we can predict collisions and something else, or X limits, etc. Here it's shown in Siemens NX. Here we see the usage of the VNCK, the kernel of the 840D, which is here seen on a simulation environment. Here you can see the complete machine with the forming tool, etc. And on the right side of the picture, here on that area, we can see the virtual control with all your values. It's like the real machine with all with all the parameters, with all the speeds, with all the X limits, and so on. And here we see the actually NC code program line, which is loaded to the machine. On this slide, we now look at the Rotorblade in the production environment, which is produced with the machine I've just described before. And in this case, we saw the application of glue is planned. Here we see the glue line. Here we see the used energy factor. And we bring this all together to the programming unit. And here we use the digital twin of the product. Here from with a picture or a screenshot from the software, we see the glue feature. It's a glue feature. It's like a milling feature or something else. And we configured it in the tape station. And furthermore, we can see how an adhesive path is also defined. It's located here. Here's the adhesive path. Here are our process parameters with the profile of the glue line, etc. In other words, the path that the machine should follow in order to apply the adhesive. And that's important for the next step. Here we see the usage of the digital data of the real product. And that's where it gets really exciting. We are planning a measuring operation in the CAM area in the tape station. This measurement program will later run directly on the machine environment, on the 840D and on the blade factory cell. And this specific data set belonging to this specific rotor blade, which we see here, is then used again for programming the bonding. So it's a special program for this special part. Here we see the usage of this data sets in the manufacturing process. Based on the measurement, the software or the digital twin of the product calculates in real time the real adhesive quantity which is required, as well as the gap management. See it here in the picture. The gap management and the corrected glue paths. We adapt the glue paths to the needs of this concrete production rotor blade, manufactured rotor blade. This enables us to detect errors in bonding application much more earlier, or to avoid them altogether. I think that's a really major fact. The use of the bonding material is also optimized. That's like Heiko mentioned before. In the project, in the blade factory project, we use on the one hand the digital product twin, and on the other hand the digital machine twin with its different anti-factors for the programming, simulation, storage, and the specific, which I talked about a little bit before, the specific product data. And on this slide, we saw antifactors for ATL, for the DTP, for the pick and place, etc. But we also use other processes such as milling, grinding, and much more processes. It's based on this multi-antifactor process. So we can have a positioning unit from the blade maker project, blade factory project, and specific antifactors for the specific processes, for the specific manufacturing processes. So it's critical that we do not just look at the individual processes in isolation. That's really important. We are not looking in the individual position in isolation. The process is built on the results, or built on the results of the previous ones. That's really important, so that the digital twins continues to grow in parallel, and that's like the product in reality do the same. Now I would like to briefly discuss the usage philosophy, sorry for that word, of digital twins. Here we see on the slide the interaction between the product, machine, and the process. And here are the representation. We call it product twin, machine twin, and process twin. And the interaction of these processes can lead us to an effective manufacturing environment, especially here in a multi-process environment. And on the other hand, I will discuss where the digital data sets are generated. On the one hand, at the product that arises from design, development, and from the life cycle of the product. The data sets in the machine environment, we can define the machine parameters, etc. We can relate them to the specific product. And additionally, it is possible in the machine environment to provide a suitable condition monitoring. And in the end, for the process, it's really important, all information relating to the process can arise in the process environment, and so must be placed in relation to the production and in relation to the machine parameters. So it is important that the data recorded at different production entities are related for a defined period of time, and then often after then no longer have any direct reference. The consistent use of digital twins, not digital twin, of digital twins, brings us additional advantages. This aggregated data sets from the product can then be used for different scenarios. For example, maintenance phases or something else can be planned better and more predictably. The enrichment of a product twin also enables an improvement for the design phase, as conclusions can be drawn from the manufactured products to the design phase. So I would like to summarize today's presentation with a statement that the use and interaction of digital twins used in the blade factory machine environment, so the machine, the process, and the product twin, reflects value-adding digitalization strategy. And in the end, the use of digital twins makes it possible to significantly reduce production costs. So I look at the time, okay. Thank you very much for your attention, and I will be happy to answer your question at the panel discussion. Thank you.
Thank you very much, Lars, for your very interesting presentation. And yeah, you're correct. Of course, we'll take questions in the panel discussion. Thank you. I now have the pleasure, and I hope everybody is still able to digest more input. Please bear with us. I'm pretty sure it's worth the wait. So I have the pleasure of introducing Peter Graves, who's a senior research structural engineer with Catapult. He obtained his PhD on his work on dual axis fatigue testing of wind turbine blades. And since then, he has been working further on developing test methods, but also other fun projects, such as the one that he's presenting today. So Peter, I'm looking forward to your presentation on additive manufacturing of wind turbine blade core materials. I'm really interested in what you have to say on that.
Thanks very much. Can everyone hear me okay? I'm guessing they can, so I'll just carry on and assume I'm getting told if not. So yeah, this work is just presenting some stuff we've done on looking at additive manufacturing of core materials. So first of all, I'll just start quickly with an introduction to core materials for blades and cover off some of the issues that are seen in the field with them, and then move on to the actual work that we've done on additive manufacturing materials and how we've modeled that, and also cover some future work as well, because this is very much in its infancy, this work. So core materials are used in blades wherever you have large unsupported panels. So they're there to increase the second moment of area of the, or rather the bending stiffness of the panels so that they don't buckle. So you have a kind of low strength, low density core material sandwiched between two high strength skins. And we use different types of core materials in different bits of the blade according to the strength requirements. So the shear webs tend to have a lower strength requirement than the blade shells. And so you might use a low density PVC foam there, whereas nearer to the blade root, you might need to use balsa wood to get better compressive and shear strength properties. And these core materials are supplied in kits, as Heiko mentioned earlier, and they're cut with a grid of kerfs or just slots in the core material that allow them to conform to the blade molds as they're placed in. So typically, traditionally, we'd be looking at materials like SAN, PVC, PET, and balsa for core materials. They're typically produced from kind of slab stock and machined with these slots. And sometimes there's kind of other methods for more high curvature parts of the mold. And yeah, they're typically supplied to blade manufacturers as a pre-machined kit. So the manufacturers don't really have to do anything with these core materials once they get them from the manufacturer. So looking at a core material breakdown for a typical kind of blade of the sort of size that's being installed now. So 80 meter plus blade, you've got 100 kilogram per meter cube PVC. We've got 850 kilograms of that, and then 80 kilograms per meter cubed, 400 kilograms, and balsa wood 450 kilograms. And the maximum core material thickness in this blade is 50 millimeters. And one of the big problems with these conventional core materials is how much resin is sucked into them as you infuse the shells and the webs. So you can see there you've more than doubled the weight of the core materials themselves with resin that's absorbed into the cores during the infusion process. And in terms of cost, these numbers are from the NREL blade cost model. So $7 for a kilogram of the foam material and $13 per meter squared of balsa. So obviously different units there. But typically, if you look at a real blade, that accounts for around 20 to 25% of the blade build materials costs, which compares nicely with Heiko's numbers from earlier as well. So not an insubstantial amount of the overall cost of the blade bill of materials at all. And there's some other problems with core materials as well. The resin absorption, as I mentioned earlier, adds to the cost and the mass of the blade. The core materials are just another, so blades are kind of like Pringles tubes in they're a nightmare to recycle, and they're considerably worse than a Pringles tube. It's not just a case of having like a metal base, a cardboard tube, a plastic lid. It's like wood, thermoset plastics, fibers, all kind of mixed up together. And so it would be nice to make the core materials out of the same material that you're using for the resin of the blade, so you can kind of recover it all much more easily. And finally, a big problem with core materials is that these score marks or the kerfs act as crack initiators. When the blade is kind of bending back and forth, that causes transverse bending of the panels because the blade surfaces are curved, and so you get cracks starting to grow along these cut lines where the resin's kind of resin-rich areas in the cores. And then when these crack lines reach the skin, they start moving across, and you gradually debond the surface of the blade, and eventually that leads to visible cracks on the blade surface as that disbond gets big enough that it can kind of separate and start bending and acting as a kind of layer on its own rather than a system with the rest of the core materials and the other skin. So that's kind of why we'd like to do additive core materials, and the proposal that we've come up with is to produce kind of a kit of panels that are molded, or they're not molded, they're additively manufactured to conform to the shape of the blade mold. And one of the advantages of additive manufacture is that you could have continuous control over the cell density along the blade, so you wouldn't have to just buy kind of discrete sets of densities of different materials. You could potentially have kind of features in the cores that direct in the resin during the infusion process. We think it'd almost certainly be faster to put this material down, because you could have them kind of click together, and it would kind of be a kind of designed in such a way that you couldn't put them down in the wrong place, this kind of thing. And yeah, you'd eliminate this problem with the kerfs acting as crack initiators as well. So in order to model this idea, what we've done is we've kind of got some baseline core material properties from our Leavenmouth demonstration turbine blade. And we've looked at those properties before and after infusion. And then we've determined some, or estimated some printed material properties using a representative volume element, and then taken that up a kind of level in the scale to look at the printed structure properties from another representative volume element. And then what we've done is compared the specific strength and stiffness and properties of the additive core with a conventional core. So the elastic properties of the kind of fiber reinforced resin have been determined using ANSYS Material Designer, which is a new feature in ANSYS, I think about 2 years ago, that lets you create a representative volume element of sort of, in this case, a chopped fiber composite. And we've looked at filling that with both carbon and glass filler material. And you can see the sort of properties we're obtaining here. So we're not massively increasing the Young's modulus of the resin itself, but we think there'll be benefits in terms of interlayer adhesion, and obviously any uplift in Young's modulus is kind of beneficial. So these are the properties that we've obtained. There's a kind of pretty marginal benefit to using carbon, so potentially it would all come down to the cost modeling, which we haven't done at this stage, whether you'd go for glass or carbon filler in this core material. And then the kind of more meaty bit of this work was creating a representative volume element of the actual infill pattern. So additive manufacture, you typically have skins on it, or surfaces that represent the outer layer of the part. And then inside, you don't have a solid part, you have an infill pattern that gives you kind of different strength and stiffness properties depending on the density of that. And there's many different infill patterns that you can try. But one of the ones that looks quite promising for additive manufacture is gyroids, which is kind of a very freaky mathematical shape that would minimize the change in acceleration of the print head. Basically, it would allow the print head to move more or less in a straight line without changing direction very regularly, which is beneficial to kind of process times and this kind of thing. And also it looks like it gets pretty good properties compared to other infill patterns like a sort of square grid or something like that. So we've created a MATLAB script to write ANSYS input to create a kind of finite element model of a gyroid. And there's a command, luckily there's a command in MATLAB called isosurface that lets you generate a gyroid, a mesh of a gyroid really easily. And then we've just kind of written a script that converts that mesh into a shell element mesh in ANSYS. So with this script, we can create arbitrary unit cell sizes and wall thicknesses, and then we can test those in ANSYS as a representative volume element by applying periodic boundary conditions on each surface. What we've done is done a kind of cohort study where we've done a sweep of different wall thicknesses and different cell sizes to study the effects of these properties on the kind of stiffness and density of the printed material. And then we've related those stiffness properties to strength properties using kind of equations found in the literature for gyroids. So we're assuming that the gyroid is going to fail by collapse rather than kind of material failure. And so that allows you to kind of work up a relationship between Young's modulus and shear modulus. But we are very much aware that we need to kind of print this stuff in real life and test the real material, because it's bound to be different at the kind of scale that we're working at compared to the scale of the stuff that we found in the literature. And also you're going to have kind of interlayer adhesion issues, which mean the material has different strength properties in different directions. But this is kind of a good starter, I think, to estimate the strength properties. And what we found when we compared the gyroid structure to conventional core materials on a specific strength basis is that they really give you quite a lot of margin in terms of how well they outperform the balsa and the PVC foams that we compared them against. So you can see here in this graph, what you have is on the x-axis is the cell size in meters. So over here, you've got 0.25 meters, which would obviously be an absolutely hugely thick core material. On the left, you've got a 5 centimeter cell, which might be more realistic for, as you saw earlier, like an 80 meter blade. But I think looking at the 115 meter blade, the NREL reference blade, that's got core material thicknesses of over 100 millimeters. So yeah, you could have fairly kind of thick or large cell sizes here. But you can see the benefit is you get better specific strength if you go to a smaller cell size. But there's a bit of a question mark over that, because the cell size and or the modeling assumptions that we've used mean that you could potentially have kind of physically impossible shapes if you go to a thick wall thickness with a very small cell size. So that's something that needs a bit more investigation. But basically you can see we're sort of well above balsa, which was the best performing of the other core materials. Once you sort of account for resin uptake in the core, what does the specific shear strength look like? With this gyroid, you can really beat that with a very significant margin. So yeah, I think there's definitely a pretty strong argument for looking into this further. One of the things that we really need to look into here is the cost of this process, like how quickly we can print it, how much the machines cost, and start working up a cost model for printing out core materials that we can compare to conventional core material kits. And we're going to do all this stuff sort of over the next couple of years with our new additive manufacturing cell, which is just in the process now of being set up. The hope with this cell is that it's going to enable rapid development of new blade designs and technologies and give us the ability to print recyclable materials at high deposition rates. A bit more about the cell. It's got a 4 meter by 2 meter by 2.5 meter print capacity, so that would be more than enough to do a kind of core material panel that could be lifted by a person and placed into the mold. It's a 7-axis robot, so we're able to not necessarily put down material in layers, we can put it down kind of at an angle as well, which could potentially help improve the strength. And it's also possible to do continuous fiber systems with this system in the future as well. So that's kind of what we've done so far. The next questions are, what kind of is the optimum for this in terms of cost, and I guess also in terms of mass for the blade, because that may pass on benefits elsewhere that give you a lower overall cost in terms of LCOE. What geometries give the optimum strength cost ratio, and how long does it take to assemble in place compared to a conventional core material? And there's also stuff around materials and process, like which kind of surface features and internal features give the best skin infusion quality. Can we use the same material that we're using for the resin for infusion to print with? That would be kind of ideal scenario from the point of view of recycling. And I guess compatibility with existing things or existing matrix materials before we get to that point. And also which additive approach best works with this system, and what are the implications of kind of doing this on site? Could we improve the kind of the cost calculation by doing this within the blade factory, or does it make more sense for a supplier to do it and pass those on to the blade manufacturer? So that is everything from me, and I'm happy to take questions as part of the panel discussion as well.
All right, perfect. Thank you, Peter. Yeah, thank you very much, Peter, for your very interesting presentation. The agenda does allow us to have a 10-minute break now. I think some of us may need it. And we'll be back in 10 minutes. So that's at 12 or 11, depending on where you are. And we'll start back with the panel discussions. We'll take then all the questions to all the participants. And yeah, until then, enjoy your time and talk to you in 10 minutes. All right, welcome back from the break, everybody. Of course, since we only have this virtual room and not a real room, it's a bit difficult for me to see if everybody has really returned, but I'm just assuming that you are all disciplined. I'm very happy to welcome Paul Mckeever. So Paul is head of strategic research with the Catapult. And Paul, you and I are going to lead the panel discussion. So happy to have you with us. Paul, how should we do that? Should we start with the questions from the audience?
Yeah, I think so. I think we should always give the audience a chance to ask their questions first. I guess we've got one or two questions as well, Steffen. So, you know, thanks everyone. Thanks for giving me the opportunity to do this panel session. Steffen, I can see in the chat function there's a question from Pablo Nueva. I don't know whether there's any other ones, but maybe we could start there.
So then I guess then you can only see the ones that have been posted after you joined. But sure, why don't we start with Pablo's question? We don't have to go in that order.
Okay, so if I just read that one out quickly, Pablo's obviously thanked everyone for your presentations. Got a question for the experts in blade manufacturing. So what are the current deviations from the design which most blades suffer from? Are these material deviations, ply positioning, bondings, or geometric issues of the finished blade shape? And what are the most crucial with respect to structural integrity? So I guess who wants to have a go at answering at least part of that?
Okay, nobody wants to go first, but maybe Heiko, at least you can, as a starting point, you intentionally included some defects, and I guess you did not just do that because you felt like doing it, but there was some sort of background to that.
Yeah, exactly. That's true. Thank you. Yeah. So what? How do I put this? I mean, I've seen a few things in my blade testing days, but I can't tell too much about them. There's very often issues with what's called overbite. So when gluing the two blade shells together, I'll try to get my hands in the picture. We don't exactly match at the leading edge. That's by a few millimeters very often. We actually have a cross section of a rotor blade here. I'm going to show that later. That can be seen there. That's not a structural issue. That's just an aerodynamic issue. Then it's well, the materials sometimes, especially on balsa wood, on the core materials, there are issues, but they are mass manufactured and usually at a reasonable quality. Ply positioning, yes, especially orientation. So this wave, this undulation we have in our test spar cap, that's something we see sometimes. That's very difficult, especially if it's carbon fiber. And on glass fiber, it's the difference. The stiffness doesn't go down, the strength doesn't go down as quickly, but carbon fiber drops very fast with wrong orientation. Bondings, well, yeah, especially Lars showed these very nice measurement and adjusting the adhesive amount to the actual measurements. The closer you get to the edge, so if you say you have a bond line thickness, nominal thickness 7 millimeters plus minus 5. That's well, considering we're talking about blades above 100 meters, that's already pretty tight. But that means you have about 30% excess adhesive if you reach your nominal value. Manufacturers are trying to go down on that. So, and if they go too far, they're going to have not enough adhesive. That's a bonding issue we see sometimes. Yeah, I think that's that can also be very crucial to fatigue life, mostly. I think that's at least a few parts of that question, I hope. I don't know, Pablo is probably on mute, so he can't comment on that, or anyone else.
Yeah, I would like to add something, maybe from the experience we have with the layout process, with the production of the blade. We have found out that very often the mold data do not always correspond to the actual data of the mold, and that's why sometimes we experience some deviation in the laser projection because they're using virtual data from the mold on actual mold, in the actual mold, and we experience sometimes here also some deviations.
How many centimeters, millimeters would you say?
It's difficult to say, but this has an impact, of course, later on the accuracy of the projection. Yeah. So if you added, deviation in the mold, deviation in the calibration projection, then it will go up to, could go up to centimeters in the projection. Yeah.
No, so now that you talked about projections again, we actually have had blades here. They just forgot layers. That's sounds stupid, but happens. I mean, I'm not going to say it happens often because it doesn't, but it's also something.
And you're also not giving names away, I guess. No.
Not all of them still have the same name, but no.
Peter, I'm just wondering if you had any thoughts around structural integrity.
Yeah, I mean, I think we've covered quite a few of the issues, but certainly some of it can be mitigated by design as well as manufacturing. So like this issue with panel breathing, which kind of acts as the blade bends, it's a hollow structure. So the panels kind of bend, and that will place stresses on all the bond lines in the blade. So depending on the blade architecture, it could place kind of stress on the bonds between the webs and the shell, and certainly on the trailing edge bond. And there's stuff you can do to get around that, so you can ensure the bond line is, or I guess the geometry of the blade. There's aftermarket things people may be familiar with around that, like Ladina make a product called the D string, which connects the pressure side to the suction side just in front of the bond line to stop the stress being passed on to the bond line when that happens. And all of those issues can be made worse by manufacturing kind of problems as well. So like Heiko touched on, the bond line control is really important there. If you've got a stress concentration from the glue kind of bulging out too much, then that is going to completely change the stresses in that bond compared to what was calculated in an FE model. So yeah, I think I've seen stuff done where they have a kind of squidgy tube that runs along the trailing edge that sort of forces the bond into like a nice radiused shape rather than bulging outwards. So yeah, there's a few things, but certainly around bonding, and the issues that I mentioned around core materials as well are also kind of a bit of a problem for industry. I think that's causing transverse cracks on the blade shells quite often, this issue with the core materials.
All right, thanks to everybody. Then there's I call it a hidden question because Paul cannot see it. So this was a question by Fowles TJ. It was specifically geared towards Heiko, but maybe we can expand on it a little bit. So the original question is to Heiko: is thermal imaging a reliable technique for blade inspections whilst in service? And maybe to expand on that a little bit, I'd be curious to hear from Lars and Carsten on what your view would be on whether or not NDT techniques such as thermography could be or should be or will be integrated in a digital production twin. But maybe Heiko, we can start with your input on the technology itself.
Yeah, I have to say I haven't done that myself, and I haven't really evaluated it. So take with a grain of salt what I'm going to say now. But yeah, I've seen some very nice results. Mostly, yeah. Now I'm going to hand this over to Lars and Carsten. Mostly, they've looked at things. They knew there was something wrong, and then they looked at it and they said, "Okay, yeah, we see there's something wrong here." There's very little, and I think that's really something to do a lot more research on. Very little. Well, we're looking at the images and we can say this image is wrong. It's usually the other way around. We know there's something wrong, and okay, yeah, then we can interpret this thermal image to show that. So possibly also because well, very often these tests or these demonstrations are done with blades where the testers don't know the design, so they can't really say if this is correct by design or not. And yeah, that's basically where the digital twin would come in again.
Yes, maybe I can add something about this. This is one of the reasons why we are digitalization or have the digitalization of the processes. So by using the digital twins, we can predict many errors, like angel deviation or draping possibilities and something else. And so we have the ability to match those planning data sets to the real data sets we are get through our inspection process, like a thermographic inspection or something else. And if we connect this to data sets, there's a picture from the thermal inspection and then the planned aspects of our parameters like angel from the carbon fibers. So we can say, okay, here is an error or there's not an error. And I think only the interaction between the digital twin and the real machine and the real inspection process gives us the opportunities to analyze the errors, to look how hard is this error? Is it a really big error or it's a small error? And I think we have the opportunity, if we are using a multi-process machine, to get the digital twins through this process chain. And many errors maybe could affect at the third, fourth process step and not at the first step, so that we have the opportunity to call back our processes and look what's the effect of defect of this error. And I think that's a really, really good advantage of the usage of digital twins.
Some enhancement, thanks, Lars, from my side. And it was my question in general for the auditorium too. I think digital twin is important, and Lars showed us a good overview from my understanding how it works in the reality. But it means you used, or by using IoT, the digital twin or the wind turbine, you can be observed in operation. The data could be processed. You have to build them up and do work with them. Maybe it's changed, but from my understanding, digital twin must be product lifecycle management with all of them combined information, not in different silos, and additional, if possible, using IoT to get this data information during the machine is working. Feed them back, and this has an influence, of course, of the development, whatever else we will do in the future. And maybe please correct me, but from my understanding, this could be a challenge for IWES to realize, I will call it a holistic digital twin, where all this information will be inside. It's completely the same question as we get. If they are inside and we have this data and we know about the influence, we can work with them. Without, it depends how it's built up in the future, or maybe nobody knows about them because the data go away, whatever is. And I still think I will finish with the question for the IWES. Is it planned in the future to go more in detail with the digital twin for the PLM area? Which question? I still think it's important for the industry because look about, we would like to have a closed loop of the rotor production. And this means in reality, industry are working with IoT and they have to use them and they ask us or ask you, is it possible as a closed loop to work with a digital twin in your area?
Heiko, would you like to respond to that?
Well, yeah, I'd like to build up a digital twin. I'm looking for resources there at the moment, to be honest. So what we started out with is, yes, it's not the full holistic approach, full model. It's the but the issue is really manpower, software power that we don't have at the moment to fully run through this.
And maybe if I may add to that, I think it's also a bit of a chicken and egg problem. Maybe whether you start with the overall whole framework that integrates all the different single digital twins into a digital twin universe, or if you start by really creating the very detailed digital twins for different process steps. And currently we are pursuing the latter approach. And that actually, maybe if I can bring that question back to you, that was one of the questions I had in mind for this panel discussions. So if you think about this discussion about integrating production data, Industry 4.0, digital twins, whatever you want to call it, in your opinion, I guess it's a question to all members of this panel discussion, who, if anybody, should or will be the owner of these data and also the facilitator? So is that more a question, a task for the OEM, for tool suppliers, for engineering service providers, or is that maybe something that comes from the operator? So what is your view on that? I guess that's a question to all of you.
Yeah, and so if we have a view how are running in automotive industry, so the OEM, most of them have the backbone and they have some requirement for their supplier and gives them away and said, you have to fulfill this process. So from my understanding, of course, you need a person or you need an area who's the owner. And as you know, people knowing means power. And if you in the first steps invest in these things, it will help you for further development in this area. And I will give you another example because I was working together at universities and there's a similar question. How could we work to develop or in our education with a digital twin, with the PLM area? No chairs has a topic which is called product lifecycle management as a chair, yes? There exists mechanical engineering, informatics, whatever else, but not product lifecycle management. It's a cross-company topic from my understanding, and that's the reason it's not so easy to address them. Otherwise, if industry would like to work in the future, they need people, students, they're educated in this area. And so again, there's the hand-egg problem, as you mentioned, Stefan, earlier. Who should be the driver to do these things? So my understanding is we have to address similar at both sides. And similar like this at university too, like industry, yes. If university is not working, not educating in this area, then industry is running not so quick as they should or as they could. And this is similar, the same question for your question, Stefan. You have to drive it from both sides. And don't ask me who is the owner at the end of the day. It's not so easy to answer this question. That's my opinion.
So Carsten, just responding to what you've said there, you know, I've seen this in other presentations from, say, Kim Branner at DTU, and he's talked about digital twin isn't just for design, manufacturing, validation. It should be used for operational,
of course,
as well. And so effectively, you're using the digital twin throughout the entire life of the turbine blade. And I guess that makes it a bit more difficult as to, well, who should actually own that digital twin? Because I guess beyond the warranty period, maybe the OEM is less interested in the product.
I agree.
And maybe to add a little bit to that, because you just mentioned Kim Brenner, who we cooperate with in the VirtualWind project, which essentially has the scope of building towards a digital twin, as you just mentioned. And I guess our answer in that project is that it's really a collaborative effort between a lot of different material suppliers, several OEMs that are involved, but also, of course, research institutions. So I guess the future will tell who will finally be the owner or the owners of this type of process. But to get there, I think it's quite certain that we need to join forces. That's, at least in my point of view, pretty evident.
Steffen, I see it that way too. And your question is really, really good. From my point of view, data is the gold of tomorrow, data sets. And so I think it is really nice for every OEM to remain the data owner. I think that's really important. And all stakeholders must be connected via authorized and authenticated data streams. And the OEM have to grant the rights to use for each other. And I think that's the way to go through the digitalization strategy for the OEM. That's my opinion.
We can have a look in other industry. Look for Amazon. It's not happening with wind energy, but what's the power of Amazon? It's not about their logistic. It's not about their products. About they know about the people they develop, they buy, they sell, whatever else. So the data information, as Lars mentioned, this is important. Whoever will do this, whoever owns this, maybe not now, but maybe in 5 years, in 6 years, I don't know. You're getting a lot of power of this. And think about your advertisement. In the past, to get advertisement is about things you never need. Then they find out people looking for special things, like looking for baby clothes, whatever else. Now you're getting baby clothes advertisements, or flying, have holidays, and now looking for. So important are the dates in the future. And so I still think an OEM will be happy to have them, but he's not working with them so much afterwards. To be an owner could be, as you said, it's a goal for the future.
I totally agree.
Okay, so we've reached consensus on that topic. That's great. Paul, do you have another question?
I've just noticed, I think Arno, my good friend Arno van Vegaard, sent a question in a few moments ago. Arno, I'm not sure whether you were directing this at any particular panelist, but you're asking how do you verify the actual properties of a manufactured blade? What cracks and irregularities occur, e.g. cracks in the bonding paste? So Arno, who do you want to answer that?
This is actually going to the whole group.
Okay.
Especially all these models that are modeling the blade, the digital twins that everybody's talking about. How accurate are they? How well can they predict the properties of not just the design blade, but of blade 37 as it rolls out of the production? This is a general question, I think.
Yeah, I think that's a very important question. So some of the kind of NDT inspection techniques like ultrasonics and stuff like that, in my experience from what I've seen, I guess maybe the arrays, like the phased arrays that are used in factories are better than the handheld devices that I've seen results from, but I'm not sure they're fully up to the job yet. Because they can't deal with, or I guess you need different technologies for different areas, but you're going to have trouble inspecting core materials because these technologies only work sort of with a solid laminate buildup and stuff like that. So I think that's a really important question that maybe sometimes gets forgotten about a bit with this kind of thing. But it's one of those things that maybe gets a little easier once blade manufacturing is really, really automated. So once you have a machine head that's kind of recorded where it's traveled, figuring out where the laminate's gone and thicknesses and that kind of thing might be a lot easier than if it's kind of a guy kicking a roll of material down the blade and then trying to figure out what's happening through the thickness later on.
Yeah, I think this is that's very true, Peter. But I think we need to find some quality control process to basically feed back that information that we don't have in the ideal designed blade before we're talking about fully automated blade manufacturing, because I think we need that before it's required now, and automated blade manufacturing has been 5 years in the future since we started with it. So my take on that.
And we need something like artificial intelligence to sort out what are the really information we need and to find a regulation which we can throw out and which one are important for us. Yes, and that's another way we have to develop Siemens in the same way. Not coming directly from us, I mean, inside this project, but it's important to note. It's important for other things like too, not only for wind blades.
Yes, I think so. It depends very much on the machine environment, on the manufacturing process, and on the accuracy process of the NDT processes, etc. So I think it is really important to unite all the data in one effective system, like MindSphere or something else, or in PLM based. And then I think knowledge can be gained out of these data sets, or a mechanism of machine learning, or etc. can be applied at that manufacturing process. So I think it's really important to put the quality inspection data sets in relation to the manufacturing and to the planning processes. And then I think you have a really, really valuable process established in the windcraft sector. But I think, Heiko, it's for you. I think there's a lot of research to do.
That's good to hear that Heiko will not run out of work.
We can't complain about that yet, but yeah.
If I may, I'd like to ask a supplementary question to what Arnold's asked, and that is, I'm implying from Arnold's question that there's a concern that there can be a significant difference between the design properties of the blade and the actual manufactured properties of the blade. And it got me thinking, if we find the sophistication to actually be able to measure the actual properties of the blade, in parallel with that, would we be improving the manufacturing capability of the blade to the point where we're confident there isn't going to be much difference? Therefore, do we need to actually measure it? And is the solution in effect more about improving the process rather than being able to verify?
It's a good question. I have to think about it.
So maybe I can share my thoughts on that, and then maybe others can comment. I think you're onto something, and the question, how much should we invest in keeping the quality, let's say, perfect versus controlling for the imperfections? It's a good question to ask. Nevertheless, regardless of how perfect we become, there will always be a trade-off between, let's say, perfection, speed, and cost. So even if the process is really reliable, you can most of the time increase the speed a little bit at the cost of quality. And then it always remains pretty important to control, or to measure the quality. That would be my view on that, and I'd be happy to hear differing views.
I think that aligns nicely with Carsten's keynote this morning when he said blade manufacturing has become more professional. So from the point someone was building a blade 5 meters long, 7 meters long in his garage somewhere. He was able to basically, I don't know, they built 20 blades a year, so they were able to do 100% quality inspection. Now, these days, we have a lot more blades, but also a lot larger. So the impact of quality irregularities are much more severe, I would say. I mean, we don't lose 500 kilos or 20 kilos of blade mass, but 30 tons, 40 tons, 80 tons. Something's wrong. But on the other hand, also the numbers go up, the lot sizes. So maybe it's easier to get into a process, or worth more effort to get the process under control.
I think it's important to control the processes to minimize the quality checks, because testing is always expensive, costs time, and the sensors are very expensive, etc. And a possible detection of errors in the manufacturing field, it's much more expensive. So I think it's important to control the process, maybe with back loop to the planning processes through inline testing, and to achieve good results, and that you have no defects at the quality run. So control the process, not measure the process. I think that's really important.
And to control the process, it means you have to build up the process at first and to know about everything. Yes.
Absolutely right.
Some additional you don't know in the moment, and now have to fix up how it's run together in the future.
That's so important that we interact from the planning process to the manufacturing process, and after that to the inspection process. I think all together, if we put all them together and interact them, then we can get better results at the end.
I agree.
So I think we have some consensus there, Steffen.
All right, good. That's good. So then maybe another question, and maybe Marie, it's a good question for you to start answering that, because you talk a lot with your customers, I would assume, at least. Yeah. So how would you? We talked a little bit on how blade manufacturing has become more professional, I would say, or more industrialized. If you look into the next 5 or 10 years, how would you see the split between automation versus manual labor for blade production? Do you think there will be a point in which it becomes fully automized, or would you think that manual labor is there to stay, or what is sort of the share between the two?
I mean, I don't want the automized because of course, I mean, the laser projection systems will be used as long as the manual, we have a manual layup. The automation, I mean, I see it in the aerospace where you will, where they will be using, you know, some robots, you know, to lay the fibers. I think that will take time. That will take quite a lot of time in the wind industry, due to the conditions, working conditions, the length of the blades, the flexibility that you need. I don't think coming very soon. I mean, like to have, you know, like a robot like we have in aerospace. They are only used at the moment also in aerospace for small parts, very small complicated parts. I don't think that will come soon in the wind industry. That's my feeling. So they will first invest in this kind of laser projection system to get first automatization. It's a first step, but I think that's easy to implement and gives the best results in a short term.
Yeah, thanks. Any differing opinions or support of that opinion from the group?
I don't think this conflicts with the use of digital twins. If the results of manual work cycles should, if they also flow in the digital twin, and so we are able to support later process steps as well as if we have a full automated process. So I think we have to keep in mind that manual work processes are able to support our digital twins, and it's a little bit a mind changer, I think.
And I agree, and I think it's in the short term, it's more kind of worker assistance than fully automation.
Yeah.
What we're going for,
Yeah.
and that laser projection is a perfect example of that. Yeah.
Because with this worker assistance, we have to feed our own system to know how they have to react in the future. So it's a step in the middle, from my understanding, exactly as Marie said. Automation, you can start not directly from manual and automation. There's a step in the middle, and this step here for wind, from my understanding, exactly in this phase we are. And from the onshore to offshore, this foster a lot to go further in this area of automation with next requirements, of course.
So I guess you're not seeing full automation at this moment. You know, would anybody be brave enough to put a split? You know, do we see more than 50% automated, 80%, 70%? What's your anticipated split?
What's the unit? Is that per mass of
just
blade, or per cost, or per time?
I was thinking more percentage. You know, if you think about it, takes X amount of effort to manufacture a blade, how much of that do you see is automated against manual labor intervention? What do we think is realistic? I guess 100% automation, we don't see that at the moment.
Yeah,
So
I'm having a hard
to answer this question.
I'm having a hard time predicting that. Yeah.
It's support. Look for different industries. From my understanding, again, because we are working in different industry, if you go for airplanes, they have a big automatization.
Yeah.
NASA, Raumfahrt, whatever else, they have a similar one. If you go for marine, they have to do it because sometimes they are underwater. If something happens, they have to control it, yes? And similar in automotive. So it depends. But at the end of the day, it doesn't means every has to be 100% automatization. I'll give you an example. I knew from big shipping buildings companies, they said, we don't want to have automatization, that a person would like to have a ship and you get automatically a contract about them because they only make 2 or 3 deals in 5 years about a lot of millions. They have to have customer voice in engagement together with them, whatever else, not to lose them. So automation is the question about the point, how much you need. It's not a general prioritization. If it's really high, then it's really good. It depends from the prioritization of the company. And I know about a special, I will call it value-oriented approach. It's called Capability Maturity Model, CMMI. And from there, you get some information about return on investment, whatever else. And you have 5 different levels about automatization. And it doesn't mean you have to go for every level on the highest level. On the 5 is there the highest level. It depends. Maybe you go on the 3rd level because your priority is not for 100%. For here, it's only for 50%. And this is the question about, you can't say 100% of automatization is general good. I mean, it depends from the branch. And of course, if you go deeper in the functionality you would like to rebuild or to help to support, whatever else. This will be my answer with a view on the return on investment. You can't say holistic 100% will be helpful, because think about if you have 100% and you need a manual influence, it's not so easy to do it. So both of them have positive and negative aspects. Could be a little bit support for this answer.
I like the answer, Carsten. Thank you.
So I guess then the consensus that we can report to whoever is that the number that Paul asked for is between 0 and 100%. That's something we can agree on. All right. Yeah. Does that help you, Paul?
Yeah, I'm much clearer now. Thanks, Steffen.
All right.
For example, the NC CAD-CAM process, there's the automation should be higher, yes. But if you think about the structure for the blade, it's not so easy to deal with them. And we are not on 100%, maybe we're on 30 or 40. And this will be developed in the future. So it depends again from the process. But between 0 and 100 will be fine. Sometimes it's 150. Yes, it's important too for spare parts to know that they work if they have to work.
All right, that broadens it even more. Perfect. I think we have time for maybe one last question. I'd be interested to know how you view the development of new materials or processes. Understandably, many of the OEMs are a bit reluctant to invest huge amounts of money in blade manufacturing because Marie mentioned that they are always aiming for flexibility, and they need to ensure that whatever they invest in can also be used for the next blade generation. Otherwise, it's pretty difficult to justify the return on invest. So having that in mind, where do you see the biggest potential for innovation with regards to production processes? Do you think that's something that's more driven by the OEMs, maybe from a material supplier side, maybe from suppliers of machinery, such as you are, or is that something that has to be driven by research organizations? Where do you see that the main emphasis there?
I think we have seen that the price of the material is the absolutely driver. I think that's the major point. And if we have a cheap material, we are able to automation processes, etc. And then the wind industry has the money to invest in machines and in automation solutions, etc. But I think the price driver is absolutely the material.
And again, it's a transformation process. Henrik, you speak about, is it at research side or is it at industry side? I still think it could be helpful if the best practice from industry fit together with the innovation theory, whatever else coming from research. And if these both things go together, similar as we are working at IWES, then this is helpful for everybody. Helpful for the industry afterwards of the results, and helpful for the research to build up new ideas, to evaluate them and to go forward. And of course, to have a prototype, whatever else, to find out is this realistic to work with them in the future.
All right, perfect. I think that's a nice way to end this discussion because we also arrived at the end of the scheduled time.